Hi everyone, I'm Professor McBain. Welcome back to Chem 100. And this is Tariel, one of my two cats. As you can see, she's not so thrilled to be here today, but hopefully she will help motivate you to be excited about our next topic in the class, which is what is in water. Alrighty, so let's start talking about what is in the water. So just looking at this picture, would you drink this water? I might. But what if I told you that it contained arsenic? Yikes, probably not. What about radioactive alpha emitters? Probably not. Anything radioactive is a big yikes as well. Vanadium? What the heck is that? Probably not. About tetrachloroethylene. They always told me not to drink anything I couldn't pronounce, right? About an herbicide? Oof, no. Well, all of these have been detected in Chico's water supply. So probably at this point you're thinking, oh my gosh, I've been drinking Chico tap water. I better start a subscription to Culligan or Alhambra. But hold on a second. What you should be asking me is, well, how much was there? And how much of that stuff would be bad for me over a certain period of time? Good job. Those are really the important questions to be asking. So to tell you the truth, no water is 100% pure. I know that we've been talking about the idea of water being a pure compound, and it's true, you know, in theory, you could pull out every possible contaminant of water and be left with a pure compound. But truth be told, it's really, really difficult to get 100% pure water. And so as a result, water is usually a solution that contains just a little bit of some contaminants that might be regulated by the EPA, such as microorganisms like bacteria or protozoa or viruses. Not viruses for very long, as we've learned with coronavirus, but bacteria can definitely survive in water and propagate through water for a long time. That water might also contain some disinfectants, such as chlorine, which is meant to kill those microorganisms, but it might also have some byproducts of that disinfecting process. There might be some inorganic chemicals, which are usually like minerals. There might be some organic molecules, like some pesticides or some other solvents and things like that. If you've ever dumped rubbing alcohol down your sink, well, that's an organic molecule that you've just dumped into the sink. Some radioactive elements, I mean, you know, we obtain uranium by mining, and so radioactive elements, I mean, they occur naturally. It's natural. And so there are, you know, there's some very, very small amounts of radioactive elements that might be in water. And so, of course, the question is, how much is there? Okay, so that's going to be the first question that we ask ourselves. And so just to start things off, let's look at an example of what's in seawater, for example. So around week 4 in lab, you guys learned about a concentration unit called molarity, right, which is really moles per liter. Let me get my laser pointer. I've also got my assistant here with me, so you might need to bear with me with a couple of whispers and additions, right? So you learned about concentrations in moles per liter, right? But if we convert from moles of a contaminant to grams of a contaminant, then you can also express that concentration in terms of grams per liter. And then we get to a system that seems a little bit more easy to comprehend. But then, of course, we've got the problem that we encountered in week 2, where we've got all of these numbers that are like really, really small, and we don't have a really good feel for them. But so if we convert back from grams to milligrams per liter, then now we're dealing with a concentration called the parts per million, okay? And so water contaminants concentrations are usually expressed in units of parts per million. If you look up the Cal Water reports in your area and in the Chico area, you're going to see all of these concentrations usually expressed in ppm. I'll dig into what a ppm really is in just a moment. But if we're talking about seawater, for example, well, seawater, we usually talk about it as being like salt water, okay? And let's see, if we remember from lecture 3 that salt, like table salt is typically sodium chloride. Well, if salt water, let's see, salt water has tens of thousands of ppms of salt. Does that make sense? I sure think so, right? And then there's another salt. Have you ever heard of Epsom salts? Well, Epsom salts is magnesium sulfate, right? And so it makes sense that there might also be some Epsom salt concentrations in seawater as well. Might also be some hard water in seawater as well, so that's where we get the calcium. There might also be a bit of potassium. There might be a little bit of baking soda, right? So all of these things seem reasonable, and it also seems reasonable that whatever the heck this concentration unit means, there would be a lot of salt. Go figure. Okay, let's dig into the definition of the ppm real quick. So a ppm is normally reported by mass, okay? Part per million is what ppm stands for. And what it really means is that there's 1 unit of mass of the solute, that's the stuff that is dissolved, for every 1 million units of mass of the entire solution. So that would be the salt water, okay? So a ppm would be very small. So 1 ppm would come out to being 1 milligrams of solute per 1 million milligrams of solution. And if you take 1 million milligrams and you convert that to kilograms, then you end up getting 1 kilogram, okay? Now, because of the density of water being 1 gram per 1 milliliter, if you do some unit conversions, you'll also find that that 1 kilogram of water-based solution roughly comes out to about a liter of water volume. Okay? This only works with water. If instead you're dealing with an ethanol-based solution, then the density doesn't let you have this 1-to-1 conversion between 1 kilogram of mass and 1 liter of water. But just trust me that this works out fine for water-based solution. Okay. A ppm actually looks very, very small. Let's take a look at what that might be. Let's get rid of my laser pointer. All right, so here on this page, let's spread out this page. If I were to keep on scrolling, yeah, there we go. There are 1 million dots on this page, okay? I haven't even reached the end of the page. I'm still scrolling right. There's the end of the page. There's 1 million dots on this page, and one of those dots would be the 1 unit, okay? So 1 ppm would basically be the expression of one of these dots per all of the million of these dots, right? So one of these dots would be, say, a unit of salt, and the rest of the 999,999, that would be the other water, okay? So that would be the expression of 1 ppm. All right, so we can get even smaller, right? So that's 1 ppm, okay? Now 1 ppb would be even less of a concentration. It means that there's 1 unit of mass of the solute dissolved in 1 billion units of mass of solution, right? So a ppb is 1,000 times smaller than a ppm, okay? All right. So let's come back to thinking about those mineral contents. Now that we've got a feel for what the ppm is, let's take a look at some various solutes that you might find in various sources of water, okay? So let's talk again about calcium, magnesium, and sodium. So let's start over here. Again, ocean water, it makes sense that there would be a lot of sodium in ocean water, okay? Now, tap water, we wouldn't expect there to be nearly as much salt in tap water, right? So it makes sense that we go from 10,000 ppm of sodium down to 57 ppm of sodium in tap water. Now, tap water in Phoenix, there's a bit more salt content, but only twice as much salt content as there is in San Jose, certainly not thousands of times more. Okay. Now, you'll also notice that there's a bit of calcium and magnesium that's found in these water sources as well, right? And so we typically think of this as how hard the water is, okay? So calcium and magnesium make up the water hardness. Evian, Perrier, and Arrowhead are all different types of bottled waters, and you can see that they contain significantly less sodium than most tap water, but they have varying amounts of calcium in them, which is pretty interesting. Now, MRI is the daily maximum recommended intake of each of these solutes. Again, an MRI is the maximum recommended intake of a chemical by ingestion. Okay? And that's going to be our definition for this abbreviation MRI in chemistry class. Okay? So yes, if you Google MRI, you're going to get back magnetic resonance imaging, and that would be appropriate for a biology class or specifically a nursing class or a pre-med class. In chemistry, MRI means the maximum recommended intake set by the EPA. Okay, so let's go back to that slide. The MRI for calcium is about 1,000 milligrams a day. So that means like once you bypass 1,000 milligrams, then it's not so good. And maybe, especially if you double that, then that's probably a little too much calcium for a reasonable person. So here's a good question. What would be the volume in liters of San Jose water that you would need to drink in order to reach the MRI of calcium? And so go ahead and do this calculation as if you were doing it for homework and make sure to show your work. So I'm not going to do it here. I'm going to do it in our examples video for this lecture series, okay? So give it a try here and then hop over to the examples video. So you can imagine that always having to do this calculation, to convert from the MRI to the volume of water that's safe to drink, that would be pretty cumbersome for most lay people. It's unreasonable. So instead of always expressing things in terms of MRIs, which are masses, which you would have to do that concentration conversion to, instead the EPA usually sets what they call maximum concentration levels. Okay, so the idea is that it's still based on the mass MRI, right? The mass that's safe for a human to consume in one day, but then they base it on an assumption that a reasonable human is only going to consume a certain volume of water on average in a day. Blah, blah, blah. Yeah, Mommy just keeps talking, huh? And so based on that average volume of water that humans will consume in a given day, then they say, well, here's a pretty safe concentration level that we can let cities and other waterways reach of this particular solute. Okay, so these levels are determined, of course, by the EPA, but they're recommended to the EPA from the National Drinking Water Advisory Council, which is comprised of scientists and doctors. But then they also listen to representatives from water utilities, which are on the other side of the water purification process and problem, right? They're like, well, we would love to only have this much arsenic in our water, but we can only reasonably get out that much. And they also take these recommendations from environmental groups and public interest groups, states, tribes, and the general public, who of course don't want to be consuming these dangerous levels of solutes, minority and low-income communities as well, and then of course representatives of small businesses, which once again they would be on the other side of the issue, saying, well, we would love for there only to be that much of that contaminant in the water, but we can only get out this much, or we absolutely need to dispose of this much into the local creek. So we're going to talk some more about MCLs in the next series in this video. I'm going to let you all have a little snack break, and I'm going to give this kid a little bit of an attention break as well. So we'll see you in the next video in this series.